What if time does not pass the same way for everyone? What if a moving clock can run more slowly? What if distance can change, depending on how fast you are moving? These ideas may sound strange, but they are part of one of the most important theories in modern physics. In this video, we explore special relativity. We will see why the speed of light changes our understanding of time, space, motion, mass, and energy. Let us begin our journey into Einstein's special relativity. Why was special relativity needed? For everyday speeds, classical physics worked very well. In Newtonian thinking, time was absolute, length was absolute, and velocities could be added in the ordinary way. But light created a serious puzzle. Experiments suggested that the speed of light did not behave like the speed of ordinary objects. Observers moving differently still measured the same speed of light in vacuum. The Michelson-Morley experiment also failed to detect the expected ether wind. So physicists needed a new way to understand motion, space, time, and light. That new theory was special relativity. Postulate 1. The laws of physics are the same in all inertial frames. An inertial frame is a frame moving at constant velocity, without acceleration. In this example, a helicopter is moving smoothly at constant speed. A parcel is released from the helicopter. To the observer inside the helicopter, the parcel appears to fall straight down. But to the observer on the ground, the same parcel follows a curved path. So the two observers describe the motion differently. But this does not mean that physics has changed. Both observers still use the same laws of motion under gravity. The key idea is this: different descriptions, same physical law. Postulate 2. The speed of light in vacuum is the same for all inertial observers. Let us compare an ordinary projectile with a beam of light. On the left, the spacecraft moves past Earth at 0.2 c. The astronaut fires an ordinary projectile forward at 0.1 c relative to the spacecraft. To the observer on Earth, the speeds add in the familiar way. 0.2 c plus 0.1 c gives 0.3 c. But light behaves differently. On the right, the astronaut fires a laser beam forward. The observer inside the spacecraft measures the light speed as c. The observer on Earth also measures the light speed as c. It is not c plus 0.2 c. It is not 1.2 c. This is the surprising heart of special relativity: light speed stays the same, so time and space must adjust. Why does the speed of light change everything? The reason is simple, but very deep. All inertial observers measure the same speed of light in vacuum. A spacecraft observer measures light speed as c. An Earth observer also measures light speed as c. So light does not follow ordinary velocity addition. If light speed must stay fixed for all observers, then time cannot remain absolute. Distance cannot remain absolute either. Instead, time, length, and simultaneity must adjust between observers. This gives us time dilation, length contraction, and the relativity of simultaneity. That is why special relativity changes our basic ideas of space, time, and motion. Time dilation means that a moving clock is measured to run more slowly. In this example, the spacecraft is moving at a speed close to the speed of light. The clock on the spacecraft is at rest in the spacecraft frame. So, for this clock, the time measured on the spacecraft is the proper time. The observer on Earth sees the spacecraft clock moving at high speed. From Earth, the spacecraft clock is measured to tick more slowly. That is why less time has elapsed on the spacecraft clock. More time has elapsed on the Earth clock. The formula is T equals gamma times T0. Here, T0 is the proper time measured by the spacecraft clock. And T is the longer time interval measured by the Earth observer. The faster the spacecraft moves, the larger gamma becomes, and the greater the time dilation. The twin paradox begins with two twins. One twin stays on Earth, while the other boards a spacecraft. The traveling twin moves away from Earth at very high speed, then turns around and comes back. This turnaround is important, because the traveling twin changes frame during the journey. Because the two twins follow different paths through spacetime, they do not experience the same elapsed time. When they meet again on Earth, the Earth twin has aged 2 years, while the traveler has aged only 1 year. The paradox is resolved because the two twins did not follow the same path through spacetime. Length contraction means that a fast-moving object is measured to be shorter along its direction of motion. In the spacecraft's own rest frame, the spacecraft has its normal length. This normal length is called the proper length, L0. But an observer on Earth sees the spacecraft moving at high speed. From the Earth observer's frame, the spacecraft is measured to be shorter. This shortening happens only along the direction of motion. The height of the spacecraft does not contract in this example. The formula is L equals L0 divided by gamma. Here, L0 is the proper length, measured in the spacecraft's own frame. And L is the contracted length measured by the Earth observer. The faster the spacecraft moves, the larger gamma becomes, and the shorter the moving spacecraft is measured to be. The relativity of simultaneity means that different observers may disagree about whether two distant events happen at the same time. Imagine two flashes of light, one at the front of a fast-moving train and one at the rear. To the observer standing on the ground, light from both flashes arrives at the same time. So the ground observer says the two flashes happen together. But the observer inside the moving train is traveling toward the front flash and away from the rear flash. So the train observer receives the front flash first. To the train observer, the two flashes are not simultaneous. This does not mean that one observer is careless or wrong. They are observing the same two events from different frames of reference. The lesson is simple: same events, different frames, same physics. The Lorentz factor, gamma, tells us how strong relativistic effects become at different speeds. When the speed is low, gamma is very close to 1. That means relativistic effects are extremely small and usually hard to notice. At 0.5 c, gamma is about 1.155. The effects are now measurable, but still moderate. At 0.8 c, gamma is about 1.667. Time dilation and length contraction now become important. At 0.9 c, gamma rises to about 2.294. Moving clocks are measured to run much slower. At 0.99 c, gamma becomes about 7.089. This shows why relativistic effects grow dramatically as speed gets closer to the speed of light. The Michelson-Morley experiment was one of the key experiments behind special relativity. In this experiment, light was split into two beams. One beam traveled along one arm of the apparatus, while the other beam traveled along a perpendicular arm. At the time, many scientists thought light moved through an invisible medium called the ether. If Earth moved through this ether, there should have been an ether wind. That ether wind should have made light travel at slightly different speeds in different directions. The two beams were recombined to form an interference pattern. If light speed changed with direction, the interference fringes should have shifted. But no fringe shift was observed. This was called a null result. It showed that no ether wind was detected. The measured speed of light was unchanged in different directions, supporting the idea that light speed is constant. Cosmic ray muons give us strong evidence for time dilation. High-energy cosmic rays from space strike atoms in the upper atmosphere. These collisions create showers of particles, including muons. Muons are unstable particles, and they have very short lifetimes. Without relativity, most muons should decay before reaching Earth's surface. But many muons are detected at ground level. From Earth's frame, these muons are moving extremely fast, close to the speed of light. Because they are moving so fast, their internal clocks are measured to run more slowly. This means the muons live longer from Earth's point of view. As a result, more muons have enough time to reach the ground before decaying. Cosmic ray muons show that time dilation is not just an idea. It is measured in nature. Particle accelerators are powerful evidence that special relativity is needed in modern physics. In a circular accelerator, electric fields speed up charged particles. Magnetic fields guide the particles around a circular path. As the particles move faster and faster, their speeds get very close to the speed of light. At these speeds, classical physics is no longer enough. The ordinary formula for kinetic energy gives an answer that is too small. Special relativity shows that the particle's energy increases rapidly as its speed approaches c. Its momentum also increases much faster than classical physics predicts. This is why accelerator design must use relativistic energy and relativistic momentum. When high-energy particles collide, detectors measure the results and help scientists study fundamental particles. Modern particle accelerators work because special relativity gives the correct rules for particles moving near the speed of light. Atomic clocks provide another way to test time dilation with great precision. At the start, two atomic clocks are synchronized to show exactly the same time. One clock remains on Earth. The other clock is placed on an aircraft moving at high speed. After the flight, the two clocks are compared again. The clock that traveled on the aircraft shows slightly less elapsed time. The difference is extremely small, often measured in nanoseconds. But with atomic clocks, even such tiny differences can be detected. This shows that time dilation is not just a thought experiment. It is a real, measurable effect confirmed by precision clocks. Mass-energy equivalence is one of the most famous results of special relativity. Einstein's equation says that energy equals mass multiplied by the speed of light squared. Because the speed of light squared is an enormous number, even a tiny amount of mass can correspond to a very large amount of energy. In nuclear fission, a heavy nucleus splits into smaller fragments. The total mass after the reaction is slightly less than the total mass before the reaction. That small mass difference is released as energy. A second example is particle and antiparticle annihilation. When an electron and a positron meet, their mass can be converted into gamma-ray photons. So mass is not simply lost. It appears as energy according to E equals mc squared. The key lesson is this: tiny mass can mean enormous energy. Special relativity is not only a fascinating theory. It is used in modern science and technology. One important application is GPS and precision timing. GPS satellites need extremely accurate clocks, and relativistic timing corrections help keep positioning accurate. Another application is particle accelerators. When particles move close to the speed of light, scientists must use relativistic energy and momentum. Cosmic ray muons also show relativity in nature. Time dilation helps explain why fast-moving muons can reach Earth's surface before decaying. Atomic clocks provide another test. They can measure tiny time differences between clocks at rest and clocks in high-speed motion. These examples show that special relativity is not just an abstract idea. It is a working part of modern physics and technology. In this video, we covered 5 important topics about the special theory of relativity. We began by discussing the 2 postulates. First, the laws of physics are the same in all inertial frames. Second, the speed of light in vacuum is constant for all inertial observers. Then, we discussed the consequences of the second postulate. When the speed of light remains constant, time and distance must adjust. This leads to time dilation, length contraction, and the relativity of simultaneity. We also discussed some well-known experiments and observations that confirm special relativity. These include the Michelson-Morley experiment, cosmic ray muons and time dilation, particle accelerators and relativistic energy, atomic clocks and high-speed motion, and mass-energy equivalence. Finally, we looked at applications of special relativity in modern science and technology. These include GPS, precision timing, and the development of particle accelerators. Special relativity changed how we understand space, time, motion, mass, and energy. Thank you for watching.